Thanks. Okay, ladies and gentlemen, I'm Daniel, the founder of the Topsound. It's my honor to show our topics, the application of ultrasonic technology in quality control of key process steps in battery mass production lines. Firstly, I would like to briefly introduce the Topsound. The Topsound is a young tech company committed to advance the battery quality and safety by ultrasonic innovation. Our core team organized from Huazhong University since 2013 and systematically developing the battery acoustic analysis technology for more than 10 years. We formally established the Topsound in 2022, and now we hold over 80 intellectual property rights. And in the more than 2 years since we established, we have served over 50 clients worldwide, and we empowered them to develop the manufacture the better batteries through our ultrasonic technology and solutions. We dedicated focus on the battery industry from its critical demands and the growth potential, and with 20% growth annually, we think the reducing scrap rates by just 1% can generate over 10 million added profit. So monitoring and optimize the key process step to systematically improve the final yield is valuable. However, the battery, we all know that the battery's manufacturing process involves dozens of critical steps. To achieve high final yield requires excel at every single process step, but unfortunately, many critical process steps lack the inline quality detect method. That results in yield management challenge across the battery mass production. And furthermore, the battery industry has limited understanding of many process defects. But how does this gas affect the battery performance? And what's the magnitude of its impact? And how can we detect the gas defects during the battery production in line? Today, I will follow this kind of topic. We just by merging the computation modeling with the physical cell experiments, we've uncovered how gas defects degrade the batteries. And we also evaluate we added a gas void into the model. And from the model simulation, we obtained a dynamic graph of the lithium ion concentration changes with the battery charging. And as is shown, the gas bubble blocks the ion transport. That means the lithium ion must take a longer path to go into the anode during the charging. And that increases the overpotential and the battery internal resistance. And additionally, the model that reveals that the anode area that behind the bubble cannot reach 100% state of charge. That's to say that this kind of material capacity is not full used, which will lead to the decrease of the battery initial capacity. And for those bubble defects, the lithium ion concentration increased significantly. And this concentration change will alter the current density distribution of the battery and further shifting the lithium plating potential at the active material surface. And as a result, the potential at the bubble's edge drops more rapidly and easily to fall below 0 volts versus the lithium metal. And this will cause the lithium plating and lead to critical safety risk for the battery. The defects increase the bubble polarization, reducing the capacity utilization. And third, the higher current density will generate more heat. And however, we know that the bubbles are poor thermal conductor, and this will lead to a large increase of temperature non-uniformity, and which also threatens the battery safety. But all these conclusions are derived from the modeling. And the new question is, how do we validate the accuracy of the model? To validate the model, we made physical cells. We simulated the gas bubble by placing a resin film inside the cell. And this film will block the transfer of the lithium ion and electrolytes. For variable control, we placing the glass fiber separators to the same thickness into the cell to eliminate the influence of foreign object insertion on the result. The graph in the middle and the graph on the right shows the curves of voltage and temperature change with the bubble cycling. The solid line represent the simulation data from the model, and the hollow dots represent the data we got from the actual cell. And as you can see that the simulated data and the real experiment data matches well. That means our model is accuracy. And just as the model inferred, the experimental data from the actual battery also proves that the gas bubble can cause a decrease in battery capacity and increase the internal resistance and an increase in polarization also. The figure D is a set of ultrasonic data which infer that the phenomenon that the set reaction occurs preferentially in the area surrounding the defects. When we see the disassembling graph of our cell, and we can see clearly observe a very beautiful lithium plating ring formed just with a few cycles. We also did the SEM and EDS test, and both the optical photograph and the SEM and EDS analysis indicate that after charging, first, the area covered by the gas, those materials fail to reach the full charging states. There are severe side reaction and lithium plating along each of the gas defects. When we review the mechanism of how gas defects affect the battery again, we find out that a more serious problem happened. There is a positive feedback loop in the impact of gas defects on the battery, and the gas defect triggers the side reaction. The side reaction generated gas and increased the size of the gas defects, which in turn further triggers more severe side reaction. That means the impact of the initial gas defects in the initial state of the battery may lead to more severe problem than what most people assume. And the capacity accelerate attenuation process shown by the data from the model and the experiment cell also confirm the existence of this kind of positive feedback mechanism. Meanwhile, the result of ultrasonic image also indicated that the defects lead to more severe gas generation from side reaction, and the area affected by the side reaction gradually expand with each cycles. It should be noted that in order to make this result more evident, the relative large gas bubble was introduced in the both above model and experiments. But in fact, we also do a lot of research that the bubble inside the battery will be smaller, but we prove that the mechanism in the is the same regardless of the size of the bubble. So now we know that the initial gas bubble will have a significant impact on the battery performance and safety. The new question is how to detect these kind of gas defects inside the battery during the manufacturing process. Okay, because it's really hard to find out the gas defects. In the most of the case, this kind of gas will escape during the battery disassembling and leaving only slight trace. That's why few detailed studies on the gas have been conducted previously. To measure this kind of gas defects, what we do is like the hospital use a B-model ultrasound to examine the human body. We use a similar technology to achieve the non-destructive defects detect of the batteries. We have invented a pair of ultrasonic roller, and in which 128 linear acoustic arrays are packaged. We let the battery just pass through the two rollers while completing the ultrasonic scanning. Here are some real cases from our customers, and these are good sales. These are bad cases with a bubble inside the cell. We have developed an AI algorithm to automatically label, recognize, evaluate, and classify this kind of internal cell defects. What's more, in large-scale manufacturing, we also apply the ultrasonic technology to more process for inline monitoring and detection. For example, we also use ultrasonic technology to conduct the online detection of the bubble anomalies and foreign objects inside the battery slurries, and use this to control the quality of the slurry. We all know that the quality of the slurry has a huge impact on the coating process, but there is no inline detection model for suited for this kind of slurry. So we create an ring-shaped array probes to conduct online monitoring of the slurry as it passes through our probe. Our system can easily adapt to a variety of battery slurry types and is easy to install. The system can conduct real-time detection monitoring, recording, and feedback of the gas and anomalies defects in the slurry. And for another case, based on the ultrasonic technology, we have developed a corresponding equipment to meet the needs of inline detection from the infiltration process of the cell. And by removing the battery with the infiltration defects, it can help the manufacturers to ensure the quality of the battery formation step. All our equipment can be connected to mass of the factory to enable the real-time data upload and linkage. In this way, the factory can collect the information from the key process steps and train the large data model to automatically adjust the production parameters. By building this kind of closed loop control, we can ensure that the high quality process of the battery mass production. Also, besides the production line application, we also researching and applying our technology in the field of R&D and in the battery monitoring and management and in the battery recycling. So welcome to discuss in more details after the presentation. So we are Topsound. We are dedicated to driving the ultrasonic innovation for sustainable batteries where the quality meets the performance and safety. And thank you for all. Welcome to exchange idea.